This is the first in a series of 3 formal examples that's going to explore how the example we just did involving bullets coming in and hitting a wall at regular intervals can be generalized to a more correct model of an ideal gas in some container and lead to some interesting formulas connecting the temperature to the amount of kinetic energy in there and other things that we've already seen on the key concepts page, together with the ideal gas law that relates temperature, pressure, and volume. So in this example, it's saying what is the pressure inside a box of length L and end caps of area A with a single gas molecule bouncing back and forth along the length with speed v sub x. So I want to draw a picture of that. This is, again, meant to be kind of like the bullet example, except instead of bullets just being fired at regular intervals, I just have this one molecule and it's just going back and forth. So it's just bouncing in that sense. When I say v sub x there, the reason I chose that notation actually is because later on it's going to lend itself to the generalization of what if instead of just one molecule just traveling horizontally and going back and forth, what if it's one molecule out of many that is traveling in some random direction and v sub x winds up just being the component that is horizontal, because that's where we're going. But for right now it works perfectly fine for this picture. Again, this molecule just bouncing back and forth. The two ends of this container have an area A, it's symmetric, and there's a length L for the overall length of this box or container, and we're being asked to find the pressure. And it turns out we can do this in a way that's very similar to the bullet example. We can look at how the amount of momentum in this molecule as it bounces back and forth, how that momentum relates to a force through, say, impulse. The one other ingredient we need to find, because in the bullet example we said they were arriving every 2 seconds, we need to actually calculate, I think, as part of this, how often is this molecule going to bounce off of one of the end caps based on the fact that it's just bouncing back and forth at a speed v sub x, and with the width of the box or length of the box of L. In other words, a total distance that has to go between bounces off, say, the left end cap would be a total distance of 2L with a speed v sub x. So that should let us do that. This is a formal example, though, so instead of going through all of that math in great detail on the whiteboard, let's look at what the answer says, and then we can talk about it, because it talks about here the impulse of a collision with an end cap is I is equal to 2 mvx. And I think the logic behind this is we're multiplying by 2 because we're saying it's an elastic collision. So the change in momentum that is represented by that is twice the momentum that the molecule already has. In other words, it's coming maybe to the left here with an amount of momentum mvx, and then it's bouncing in the opposite direction with the same momentum mvx, but that's a total change in momentum of 2 mvx, which implies that that's the total amount of impulse that was exchanged with the wall here. The next line here is where we're calculating the time that I said we would need. And it's saying that time is equal to 2L, since that's the total distance twice. So it's going to, once it bounces here, it needs to go all the way back, bounce there, and then come back another L. So that's a distance of 2L. And since distance is equal to rate times time, that would mean 2L would be equal to Vx times t. But if you divide both sides by Vx, you get t is equal to 2L over Vx. Which then implies that if force is looked at as impulse divided by time, right? Since impulse is defined to be average force times time, this makes sense if you want to find force. And then if you plug in both of these quantities, I think a little bit of algebra happened here, because we're really doing 2 mvx divided by this fraction, but if you multiply by the reciprocal of this times this, I think the 2's would cancel, and that's why this Vx times the Vx on the bottom there gives you that Vx squared. So that explains where this expression comes from. And then since pressure is force divided by area, that becomes or simplifies to mvx squared over L times A. This L, of course, came from the L that was there in the force expression, but I simplified it together with the area in the denominator from the definition of pressure. What's cool about that, though, is that length times area really is the volume of this box. So that's what happened here in this last step. On the third line, that is, maybe it's not the absolute last step, is that L times A is equal to volume. And then I'm suggesting at the end here, this really is the answer, I think, to the question as posed, because it just asks for the pressure for a single molecule based on the given quantities, although I didn't give M, but the molecule has to have a mass M, so we're being maybe a little vague here with this. But if you increased this, so if we already started to relax this picture a little bit, or maybe make this picture a little more realistic, instead of just one molecule bouncing back and forth, what if there were n molecules bouncing back and forth? Then the pressure would be equal to this expression here.